today is going to be hopefully a very simple addition to the skills that we've been learning. Although it's a little bit odd, because the way that you're used to interpreting graphs, we kind of have to flip that on its head just for the moment. Not really flip it on its head, but just take something into consideration. So the learning intention is simply to interpret the graph of the derivative function. Just to interpret. The success criteria is I can identify a derivative graph, but I can also create a graph from of a derivative function from a function itself. So, what I want you to do is to consider the graphs of x cubed and negative x cubed. We've used cubics quite a bit, and they look like these two on the left and the right. Yes? All right. What is the gradient function, for everyone who was here yesterday, what does the gradient function of f of x look like? Not the graph of itself, but what is, if I was to say f of x equals 3x squared, and this guy here, g of x. So g of x is negative x cubed, so the reflection of that graph. Then the gradient function of graph g, function g would be negative 3x squared. Okay. So what we learned yesterday was a skill to be able to differentiate that algebraically. So this is just a quadratic function. Do we know what this looks like? Hey mate, I'll sign it in a second. Give me 10 minutes. Okay. So our formulas are still here on the board. So as we can see, does this actually look like 3x squared?
Yes.
Yes, it is. So what we have here is a comparison of the two graphs. A cubic function here, an inverse cubic function, yields a quadratic and a quadratic here. Okay, well that makes sense. If we can differentiate and we obtain a function, then we can plot the function. But where does this actually come from? Well, the way that we think about this is drawing what's called a sign diagram. Very, very simple, very incredibly simple and really useful. What does the gradient look like from here to between these purple lines? Is it positive or negative? Is the graph itself increasing, going up, or decreasing, going down?
No,
it's increasing. So from here, it's increasing the most. So on my sign diagram, it's increasing. It's still increasing, but it's increasing by smaller amounts. And then at this point here, x equals 0. What is the gradient at this point? 0. It's referred to as a point of inflection, POI. And at the point of inflection, the gradient is 0. What about on the right-hand side of the point of inflection? Right here. Is it going up or going down? Up, which means the gradient is increasing, or in terms of positive or negative? Positive. So our gradient is increasing. Now, let's make a link between what we've just drawn on the sign diagram and the quadratic here. This is saying that the gradient is positive, 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 0, positive, positive, positive. Is that reflected by this graph?
No.
Yes, it is. Because this is actually a graph of f dash of x against x. And what we can see about this, the curve itself, is it always above the negative? Yes, the negative region's down here. So it exactly touches at 0, which means that this gradient function hits 0 once at x. So in other words, what we can say about the sine diagram, this function below will be in the positive region from negative infinity to 0. Then at 0, it will be this point of inflection, and the point of inflection, a gradient of 0. A gradient of 0 means the gradient function will touch 0. And then on the right-hand side, the gradient is positive again. What does that look like on the graph of the gradient? Just means it's in the positive region. So that's quite crazy to think about. Let's try this one. What's a sine diagram? So just like what I've drawn here in purple, look like for this one over here. Decreasing, so the gradient's decreasing. So let's say it's decreasing largely, and then gets to 0, we have a point of inflection at 0 again. And then decreasing again, but kind of the gradient is getting steeper and steeper. So how does this look like when we plot this graph? Well, this is on the vertical axis, the y-axis, this is actually a plot of g dash of x, or the gradient function. On the x-axis, we have x again. And the way that this sine diagram can help us is that the gradient function will be in the negative region from negative infinity to 0. It will touch the x-axis at 0, and then it will return back into the negative region again after 0. Any questions about that? Because the biggest kind of link is to see, well, okay, we're graphing kind of the next order. And the thing I want you to think about, the only time we've done this so far is when we've used the discriminant to get a graph of the discriminant versus x. Way back in quadratics. That's the only other time I've done this. And it was done not as well as I'd like, but... So let's summarize this here and then tackle some examples. So, in summary, where the graph is positive, so the graph of f of x, its gradient has positive y values. Where the graph is negative, the gradient function has negative y values. And where the graph is neither, the gradient function has 0 y values. So it could be y values in that a gradient function won't always be a quadratic. It could be of higher order, we could have multiple 0 values. Alright, so if I can scroll down just a touch. Alright, our first example here. For the graph f, find the x values where the gradient function is greater than 0. So I might just write in English what we're being asked for, just for the first one. We're being asked to find x values where gradient function, or the derivative, is greater than 0. In other words, is positive. Now, of course, these characters here is much easier to write than this, which is why we do it, but we want to be able to interpret that this is actually the same. So, just looking at this graph, because this is a graph of y against x, where is the graph increasing? Going up. Between? I heard it the first time. Alex, was it? Right, it's between these 2 points. So, the x values would be? Yep, so let's say part A for x is between -1 and 5. Between those points, the graph is increasing. What about the second one? Can I just have a volunteer? What's the second one in plain English asking us?
X values when the gradient function is less than 0.
That's right. So in less than 0, where is the gradient function going to be negative? Or in other words, where is this graph decreasing?
When x is smaller than -1 and greater than 6.
Yep, so you've said, because there's two ways of writing this. So you've said where x is no. Alright, well let's write it the way I wanted to write it first. So from negative infinity to -1 and 5 to infinity. But you could have, like what you've said was with x is less than -1 and x is greater than 5. Two different ways of saying the same thing. And last of all, another volunteer, what's this asking?
Is equal to 0 when the values of y are equal to 0.
Right. When is our gradient function going to be equal to 0? So can we see any points on this graph where we have a gradient of 0?
At the turning point,
Yep.
-1, -7, and 5 and 6.
Yep. So the x values would be
-1 and 5.
okay. So linking back to our learning intention, we're interpreting what the gradient function is going to look like without actually having the function there. We haven't derived this function, we haven't even been given it, but we still have a good picture of what it's going to look like. And what we're going to do in the next 3 examples is sketch that to the best of our ability. Okay, make sure you've got a ruler. Okay. So let's do the first 2. Draw up a couple of quick axes.
Quinn, where's the funniest?
Alright, now I just want to put some labels on these axes, but I want to do that in just a minute. I'm making a point about the labeling the axes because that's where people often make mistakes. Sketch the graph of y equals f dash of x. So that's telling you we're putting the gradient function in place of y for each of the following. And then in brackets, it is impossible to determine all features. So there's a few aspects of the graph that we won't be able to get. So the gradient function and the original function are both going to share the x-axis. If this is the graph of y against x and y is equal to f of x, then what's this vertical axis going to be represented by?
F dash of x.
F dash of x. So it's still the y-axis, but it's not representing the original function. It's going to represent the gradient function. This one here, same again. All right. Now, let's have a look at our key features we've got here. We have x-intercepts at 2 and 4. We have a turning point at 3. What about a sine diagram? Sine diagram. What does it look like for this quadratic here? I'll also start drawing the sine diagram over here. Positive or negative? Negative. What about at this point here? 0. And then? Positive. Okay, so what type of graph is going to be, will only have one x-intercept and go from negative to positive?
Linear.
Linear. Where is it going to go through the x-axis?
3.
Pardon?
3.
3, right. So it's going to go through at 3, and it's going to be a linear graph. Okay. Can we determine any other information? No, we can't. I'll be with you in a second, guys. Yeah. I've got 2 examples to go.
We get.
You good?
We do.
All right. What about this graph here? Sign diagram? Positive? The whole way?
Yeah.
All right. So the sign positive the whole way, which means it's not going to ever cross the x-axis. And with a straight line, we've been given 2 points here. Can we determine what the gradient is? 1. So if the gradient of this line equals 1, and it only stays in the positive domain, then it must be a horizontal line that forever stays in the positive region. All right, sorry about the delay. Any questions with those 2 before we move on? No? All right. Well, then the last one is going to require a little bit more finesse. So, here we go. While I'm getting set up, draw your sign diagram. Draw your sign diagram for this odd-looking cubid. Okay, what's our sign diagram look like from here to here? Positive? And then at this point here? No, sorry, I mean exactly at this point. Right, we have a turning point. Point of inflection or turning point means the gradient is going to be 0. And then in between these 2 points, negative. And then at this point again. And then on the other side of the point, positive. So, what's a graph going to look like that comes from the positive region, goes through 0, dips into the negative region just for a little bit, and then turns around and comes back out into the positive? Quadratic. Do we know that where these 2 points are on the x-axis? They are at, this one is? Negative 1.5. Negative 1.5. And the other one? 1. Ideally, I'll be using a ruler. And then we know that it's coming down from the positive, going into, and then coming out like this. And we do not have enough information to find anything else about this graph. We know its shape. We can't find its turning point or the y-intercept. We haven't been given enough information. And that's our last example for today. So hopefully, sign diagrams, really useful. You don't have to always use them, but it's a really, simple way of visualizing what the graph's going to look like. All right. So, 17D, questions 1 to 7, and then 9. Most of it is multi-choice at the beginning. You won't have to do too much graphing, but then towards the later end, they'll ask you to graph just like what we've done here. Thanks, everyone.